You pull every atom from a box, every molecule, every particle, you seal it. Perfect vacuum, nothing inside. Absolute zero. Empty space. Except it is not empty, not even close. Between those walls, something churns, something flickers, something pulls and pushes with forces we can measure on kitchen countertops. The quantum vacuum is not a void. It is a seething storm of creation and destruction happening faster than thought itself. And what we have learned about this storm is stranger than any science fiction you have heard. Same energy, no difference. Lamb and Rutherford find a gap, 1058 megahertz. A tiny shift, but it should not exist. The Shelter Island Conference happens weeks later. June 1st through 3rd, physicists gather at the far end of Long Island. Lamb presents. The room goes quiet. The best theory in physics just failed. Hans Bethe takes the train home to Schenectady, 75 miles. He works the entire ride. By the time he arrives, he has an answer. The electron interacts with the vacuum, not with emptiness, with something. 0-point fluctuations. The electromagnetic field, even at its lowest energy state, vibrates. Those vibrations shake the electron. They blur its position. The S-state electron spends more time near the nucleus. The vacuum pushes it. Energy shifts up by 1086 megahertz. Vacuum polarization pulls it down 27 megahertz. Net result matches Lamb's measurement. This is not theory fixing itself with invisible magic. This is the vacuum doing work we can see. Also, this script is researched and factual using sources from Physical Review Letters, Volume 72, published June 18, 1947, where Lamb and Rutherford first reported their hydrogen spectrum measurements, and from the Nature Journal article, Volume 479, published November 16, 2011 by Wilson and colleagues at Chalmers University, demonstrating the Dynamical Casimir Effect, which we will discuss in detail. These are not popular science summaries. These are the original experimental papers where the measurements happened. Now back to the information. Virtual photons pop in and out everywhere. Between the plates, only wavelengths that fit whole numbers can exist. Outside the plates, all wavelengths exist. More modes outside than inside. Pressure difference. The plates attract. How much? The force per unit area equals pi squared times Planck's constant times the speed of light divided by 480 times the separation distance to the fourth power. At 10 nanometers between 1 square meter plates, the force equals approximately 133,000 newtons. At 100 nanometers, you get 133 newtons. At 1 micron, you get 0.133 newtons. The closer they get, the harder they pull. Steve Lamoureux measures it in 1997. He uses a sphere and a plate, aluminum coated, separation between 0.6 and 6 microns. Torsion pendulum detects the twist. Agreement with theory within 5% experimental uncertainty. Umar Mohideen repeats it in 1998. Better precision. The Casimir force is real. Metal plates feel the quantum vacuum. Energy density of the vacuum matters. Robert Jaffe at MIT publishes a paper in 2005. Title, in the archive, The Casimir Effect and the Quantum Vacuum. He argues the opposite. Casimir forces exist without reference to 0-point energies. They are relativistic quantum forces between charges and currents. The force vanishes as the fine structure constant approaches zero. The standard result corresponds to the fine structure constant approaching infinity. The Casimir force is the retarded van der Waals force between metal plates. Which interpretation is correct? Both calculations give the same number. Both match experiment. The mathematics works either way. The ontology remains disputed. Does the vacuum contain real energy that pushes? Or do the plates interact through quantum field correlations without invoking vacuum energy? Experiments cannot decide. They measure force, not interpretation. But one thing is certain. The vacuum between those plates behaves nothing like emptiness. Tunable electrical length, they attach a squid, superconducting quantum interference device. They modulate the squid's inductance at 11 gigahertz. The electrical length of the transmission line changes at a few percent of the speed of light. This is the key. Gerald Moore predicted this in 1970. A mirror moving at relativistic speeds converts virtual photons into real photons. Actual mirror? Impossible. You cannot accelerate metal to near light speed, but electrical length? That you can change. The vacuum sees a moving mirror. Virtual photon pairs normally appear and annihilate instantly, energy borrowed from uncertainty, returned before the universe notices. But when the mirror moves fast enough, some pairs separate. One photon escapes. The other escapes. They do not recombine. They become real. The experiment runs. Temperature near absolute zero. The team detects microwave photons. Light created from vacuum. Not metaphorically, actually. Photons that did not exist before. Photons with measurable energy and frequency. The Dynamical Casimir Effect observed for the first time. Published in Nature, volume 479, pages 376 through 379. They also detect two-mode squeezing, quantum signature, pairs of photons with correlated properties. This is not classical radiation. This is quantum vacuum fluctuations made manifest, but measurable. Real? The energy comes from the squid. The vacuum provides the mechanism. Without quantum fluctuations, this experiment produces nothing. With them, you get photons, the most direct observation of vacuum particle creation we have ever achieved. Observations later show the universe expands. Einstein calls it his greatest blunder. But the cosmological constant comes back. 1998, Saul Perlmutter, Brian Schmidt, Adam Rees. Supernova observations. Type 1, a supernovae at high redshift. They are dimmer than expected. The universe's expansion accelerates. Something pushes space apart. We call it dark energy. 70% of the universe's energy content. The simplest explanation? Vacuum energy. The cosmological constant is not zero. Its value is approximately 10 to the negative 9 joules per cubic meter. Tiny, but not zero. The calculation gives 10 to the 113 joules per cubic meter. Observed value? 10 to the negative 9. The theory exceeds observation by 10 to the 122. 120 orders of magnitude. This is the cosmological constant problem, called the worst theoretical prediction in the history of physics. 60 years of work. No solution. Yakov Zeldovich points this out in 1967. Every quantum field fluctuates. Each contributes to vacuum energy. The sum should curve space-time violently. The universe should collapse to a point or expand so fast atoms never form. But we exist. Galaxies exist. The observed cosmological constant is almost exactly zero. Almost, but not quite. Just enough to accelerate expansion now after 13.8 billion years. Why? It is a mathematical artifact. You can choose a different zero. Shift the energy scale. Make it vanish. But general relativity cares about absolute energy, not differences. A non-zero vacuum energy gravitates. It curves space-time. The cosmological constant measures this curvature. We cannot just set it to zero by choice. Others propose supersymmetry. For every boson, a fermion. For every fermion, a boson. Bosons contribute positive vacuum energy. Fermions contribute negative. Perfect supersymmetry gives exact cancellation. Net vacuum energy, zero. But supersymmetry is broken in our universe. We do not see superpartners. If supersymmetry exists, it breaks at high energy scales. Low energy vacuum energy does not cancel. The problem remains. Multiverse proposals say different universes have different vacuum energies. We live in one with a small value because only such universes allow life. Anthropic reasoning, uncomfortable for many physicists, not predictive. Others modify gravity, unimodular gravity. Vacuum energy does not gravitate. But this creates new problems. Every proposed solution either fails or introduces new mysteries. If cosmology is right about the cosmological constant quantum field, theory is wildly wrong. Both theories work everywhere else. Quantum electrodynamics predicts the electron magnetic moment to 12 decimal places. General relativity predicts gravitational waves and black hole mergers perfectly. But vacuum energy? Total breakdown. The largest failure of theoretical physics. The Lamb shift measures 1057.845 MHz in the most precise experiments. Lundin and Pipkin in 1981. Agreement between theory and experiment to better than 1 part per million. Theory includes vacuum polarization. Virtual electron-positron pairs appear near the proton. They screen its charge. The electron sees a slightly different electric field. Energy shifts. The calculation uses quantum electrodynamics, Feynman diagrams, electron self-energy, vacuum polarization loops, finite nuclear size corrections. The proton is not a point, and it has a radius of approximately 0.84 femtometers. All these effects matter, all calculated, all measured, all match. The quantum vacuum is real in these experiments. Its effects are measurable and predicted, but scale up to the universe. The same vacuum energy calculation fails by 120 orders of magnitude. General relativity does not let you ignore it. Every energy gravitates, including the energy you subtracted. Some argue the vacuum energy should exactly cancel by some unknown symmetry. Others say we are missing physics, new fields, new particles, new principles. Dark energy might not be vacuum energy at all. It might be a field that changes with time. Quintessence, scalar fields rolling down potential. But observations so far favor a cosmological constant. Energy density that does not change as the universe expands. This fits vacuum energy, but the value is wrong. Optical dynamical Casimir effect and dispersion oscillating fiber. These experiments keep confirming quantum vacuum effects. Every test works. Predictions match. The vacuum is active. It fluctuates. It creates particles. It pushes objects. But the cosmological constant problem does not budge. The atom couples to vacuum fluctuations. Energy transfers. Classical electrodynamics predicts excited states are stable. Quantum electrodynamics says they decay. Measurement agrees with quantum theory. The vacuum causes emission, magnetic moment of the electron. predicted by Dirac equation to be exactly 2 Bohr magnetons. Measured value is 2.00231930436. Theory calculates corrections from vacuum loops. Electron emits virtual photon. Photon absorbed. The electron wiggles. Magnetic moment changes. Calculation matches measurement to 12 decimal places. Most precise prediction in physics, all from vacuum fluctuations. Approximately 1.32 times 10 to the 18th volts per meter. The vacuum breaks down. Electron-positron pairs appear. Virtual pairs become real. The field provides energy. Uncertainty allows the fluctuation. Strong field prevents recombination. Pairs separate. Permanent creation, not observed yet. Field strengths too high. But the calculation is there. Quantum chromodynamics, vacuum, quark, and gluon fields. Bag models of hadrons. Quarks, confined inside. Casimir energy of the vacuum contributes to proton and neutron mass. Approximately half the mass comes from vacuum energy inside the hadron. The other half from quark motion and gluon fields. The vacuum is not a passive background. It is an active component of matter. Near the event, horizon vacuum fluctuations create particle pairs. One falls in, one escapes. The escaping particle is real radiation. The black hole loses mass, temperature inversely proportional to mass. Smaller black holes radiate faster. A black hole with the sun's mass has a temperature of 60 nanokelvins, undetectable. A black hole with the mass of a mountain radiates at room temperature. A microscopic black hole radiates at billions of kelvins. It explodes, all from vacuum fluctuations at the horizon, not observed yet, but the theory ties vacuum fluctuations to gravity and thermodynamics. The vacuum determines black hole entropy. Acceleration of 10 to the 20 meters per second squared gives a temperature of 1 Kelvin. Enormous acceleration, not achievable, but the principle is clear. The vacuum state depends on the observer. What looks empty in one frame teems with particles in another. The vacuum is relative. What drives this? Vacuum energy. A scalar field in a false vacuum state. High energy density, negative pressure, space expands. The field eventually decays. Inflation ends. The universe enters the hot Big Bang phase. But during inflation, vacuum energy dominates. Quantum fluctuations in the inflaton field seed structure, density perturbations, these grow into galaxies. The cosmic microwave background shows these fluctuations. Temperature variations of 1 part in 100,000. They come from quantum vacuum fluctuations stretched to cosmic scales. The vacuum creates the universe's structure, flatness, horizon, monopole. But it does not solve the vacuum energy problem. It makes it worse. The inflaton vacuum energy during inflation is approximately 10 to the 60 joules per cubic meter, much larger than today. What reduces it? Phase transition. The field rolls to a lower energy state. Fine. But why does it roll to almost exactly 0 and then stop at 10 to the negative 9? The tuning required is extreme. 1 part in 10 to the 120. No known mechanism explains this. Observations constrain this. The equation of state parameter W equals pressure divided by energy density. For cosmological constant, W equals -1 exactly. Measurements give W equals -1.03 plus or minus 0.03, consistent with cosmological constant within error. No evidence yet for evolution, but the search continues. 3 materials with specific dielectric properties. Calculation shows repulsion is possible, not measured yet convincingly, but theoretically allowed. Applications in micro and nanomechanical systems. MEMS devices experience Casimir forces at small scales. They cause stiction. Movable parts stick together. Engineers must account for this, design around it, or use repulsive forces to prevent sticking. Quantum levitation. Objects suspended by vacuum forces. Not science fiction. Possible in principle. Energy extraction from vacuum. Patents exist. 2002. Device to capture charge from Casimir plates. Store in battery. Does it work? Unclear. Energy must come from somewhere. The vacuum does not provide free energy. You do work changing the boundary conditions. That work becomes photon energy in the Dynamical Casimir Effect. You do work modulating the squid. Photons appear. Energy is conserved. The vacuum provides the mechanism, not the energy. Photons with wavelengths comparable to temperature contribute. Finite conductivity corrections. Real metals are not perfect conductors. Drude model. Plasma frequency. All these effects measured. All included in theory, all match. The Casimir force is the most precisely tested manifestation of vacuum energy at the tabletop scale. Quantum fluctuations limit sensitivity. Heisenberg uncertainty. Measuring position disturbs momentum. Quantum noise, shot noise, and radiation pressure noise. The vacuum fluctuations of the gravitational wave detector itself set limits. Squeezing helps. Correlated quantum states. Reduce noise in one quadrature. Increase in another. Net improvement in sensitivity. LIGO uses squeezed light. Vacuum fluctuations, engineered to improve detection. July 2020. Nature Journal. Quantum vacuum fluctuations influence motion of macroscopic human-scale objects. LIGO mirrors. Correlations below the standard quantum limit measured. Direct observation of quantum effects at kilogram mass scales. The vacuum reaches from atoms to LIGO. Energy and momentum do not satisfy the relativistic relation. It exists for a time allowed by uncertainty, then disappears. Higher order corrections. Virtual photon becomes virtual electron-positron pair. Then back to photon, even higher orders, more virtual particles. The series converges, each term smaller. Perturbation theory works. The virtual particles are mathematical tools. Or are they? The Lamb shift says they are more. The Casimir force says they are more. The dynamical Casimir effect says they are more. They have measurable consequences. They do work. They are real in the sense that they produce observable effects. Whether they exist between measurements is a question of interpretation. Copenhagen says no, the system is in a superposition. Many worlds says yes, all possibilities are real. Pilot wave theory gives a different answer. Virtual particles guide the real particle. The ontology is unclear. The predictions are not. This is not a failure. This is a feature. It connects quantum mechanics to gravity. But it makes defining vacuum energy difficult. Which vacuum? Which observer? The stress energy tensor depends on the state. Different states give different energies. The cosmological constant problem becomes even harder. In flat space-time, we have one vacuum. In curved space-time, we have many. Which one gravitates? Energy equals 1/2. Planck's constant times frequency. Unavoidable. Ground state energy. You cannot remove it. Try to localize the particle. Kinetic energy increases. Try to stop the particle. Position uncertainty increases. Potential energy increases. Minimum energy is non-zero. Quantum mechanics requires this. Extend to fields. Every field mode is a harmonic oscillator. Infinite modes. Infinite energy. Regularization. Cutoff. Sum up to some maximum frequency. Energy is still huge, but finite. Renormalization. Subtract the infinite part. Keep finite differences. This works for interactions. Does not work for gravity. Gravity couples to total energy, including the infinite part. No way to subtract it. The cosmological constant problem in its purest form. Couple them to transmission line resonators, cavity quantum electrodynamics, Jaynes-Cummings model, controllable quantum systems, strong coupling, weak coupling, ultra-strong coupling, vacuum Rabi splitting, the atom and cavity hybridize, new eigenstates, energy gap, even when no photons are present. The vacuum state contains structure, observable in the spectrum. These systems let us explore vacuum physics in the lab. Tunability, scalability, programmable interactions, quantum simulators for vacuum effects. The Chalmers experiment that produced the Dynamical Casimir effect is one example. Others will follow. Standard candles, measure luminosity distance, cosmic microwave background, Planck satellite, measure temperature fluctuations, acoustic peaks, constrained cosmological parameters, weak gravitational lensing, galaxy shapes distorted by dark matter and dark energy. All these observations constrain vacuum energy. The value is small, the evolution is slow if it exists at all. The cosmological constant fits best. But that makes the theoretical problem worse. Why is it so small? No answer yet. Or is momentary existence enough? Quantum mechanics blurs the line. Classical physics has definite states. Quantum physics has superpositions, probabilities, potentialities. The vacuum embodies this. It is potential becoming actual for an instant, then returning to potential. The quantum vacuum is the most fundamental manifestation of quantum uncertainty. The universe expands, but not too fast. Structure forms, galaxies, stars, planets, life. The vacuum energy must be small enough to allow this. If it were much larger, the universe would have expanded too fast. No galaxies would form. If it were negative, the universe would have collapsed. The anthropic argument says we exist, therefore the vacuum energy is small in our universe. Other universes might have different values. We cannot observe them. In our universe, the value is tuned. This is not an explanation. It is an observation. The explanation remains unknown. Perhaps vacuum energy is not what we think. Perhaps space-time is emergent. Perhaps quantum mechanics is incomplete. Perhaps the cosmological constant is a window to new physics. The Standard Model and general relativity are both incomplete. They do not include each other. Quantum gravity remains elusive. String theory, loop quantum gravity, causal dynamical triangulations, asymptotic safety, none proven, all speculative. But all attempt to unify quantum mechanics and gravity. The cosmological constant sits at this boundary. It is a gravitational effect of quantum vacuum energy. Or it should be. That it is not, is the puzzle. They parameterize a covariant framework connecting Casimir effect measurements to gravitational coupling. Next generation Casimir experiments might explore this parameter space. if the quantum vacuum energy contributes to local gravitational vacuum energy density, if change in gravitational coupling implies change in cosmological constant. Experimental tests are possible. Not easy, but possible. Precision Casimir measurements with gravity detectors has not been done. Could reveal new physics. Energy that might not exist, or might be infinite, or might be almost zero. Forces measured to parts per million. Cosmological constant wrong by 10 to the 120. The most precise science, the worst prediction. Both true simultaneously. It creates gravitational effects we cannot calculate. It drove cosmic inflation. It accelerates the universe today. We measure it. We use it. We do not understand it. This is not a failure. This is the frontier. The place where our best theories break, where new physics waits. Every major revolution in physics came from a breakdown. Blackbody radiation led to quantum mechanics. Mercury's orbit led to general relativity. Vacuum energy breakdown will lead somewhere. We do not know where yet. Standard result corresponds to fine structure, constant, approaching infinity. This interpretation removes vacuum energy from the Casimir calculation. But the Lamb shift still needs vacuum fluctuations. The electron magnetic moment still needs vacuum loops. Hawking radiation still needs vacuum pairs at the horizon. The dynamical Casimir effect still creates photons from vacuum. Removing zero-point energy from one calculation does not remove it from physics. It shows we have multiple ways to calculate the same answer. Which interpretation corresponds to reality? Experiments cannot tell. Mathematics gives the same result. Nature does not care how we calculate. Nature cares what is measurable. The Casimir force is measurable. Plates attract, metal moves, that is real. Whether we call it vacuum energy or relativistic van der Waals forces is semantics. The force exists. But the cosmological constant problem does not go away, because general relativity couples to the stress-energy tensor, and the quantum stress-energy tensor of the vacuum in flat spacetime is proportional to the metric, a cosmological constant. Calculate its value from particle physics. Get 10 to the 113. Measure it from cosmology. Get 10 to the negative 9. The discrepancy is not language. It is a prediction failure. Some physicists propose the vacuum energy is infinite but does not gravitate due to unknown symmetry. Others propose it is finite but screened by quantum gravity effects. Others propose space-time is emergent, and the question is ill-posed. Others propose we live in a multiverse and anthropic selection explains the value. Others propose new fields or modifications of gravity. 70 years of proposals, none successful. The cosmological constant problem remains the hardest problem in theoretical physics, not because we lack ideas, because we lack a way to test them. The energy scale of quantum gravity is the Planck scale, 10 to the 19 giga-electron volts. The Large Hadron Collider reaches 10 to the 4 giga-electron volts, 15 orders of magnitude too low. Direct tests are impossible. Indirect tests are subtle. The cosmological constant is one of the few windows to Planck scale physics. That is why it matters so much. Repulsive Casimir force is theoretically possible, not yet achieved reliably. Quantum computing, superconducting qubits coupled to vacuum fluctuations, decoherence, relaxation, dephasing, all involve the vacuum. Controlling vacuum modes improves qubit coherence. Cavity quantum electrodynamics, Purcell effect, enhanced emission, suppressed emission, quantum networks, quantum communication, all rely on understanding vacuum interactions. The quantum vacuum is not just fundamental physics, it is technology. Use it. Understanding grows each year. We have measurements, all agree. But the why remains hidden. Bohr said, shut up and calculate. It worked. The calculations give the right answers. But physicists want more. They want understanding. The quantum vacuum is at the center of this desire. It forces us to confront what reality means, what existence means, what emptiness means. Turns out, emptiness is full. Nothingness is something. Vacuum is a plenum. This is the quantum world. Final calculation. Total zero-point energy in a cubic meter. Sum over all modes, photons, electrons, quarks, neutrinos, W bosons, Z bosons, gluons, Higgs bosons, cut off at Planck frequency. Integral diverges. Use Planck energy. Maximum energy per mode. 1.2, 2 times 10 to the 19 giga-electron volts. Convert to joules, multiply by mode density. Sum up, get 10 to the 113 joules per cubic meter, divide by the speed of light squared. Get mass equivalent, 10 to the 96 kilograms per cubic meter. For comparison, the average density of the universe is 10 to the negative 27 kilograms per cubic meter. The vacuum should be 10 to the 123 times denser than everything we see. The universe should be dominated by vacuum energy. It is, kind of, but the wrong amount, by 120 orders of magnitude. This is not a small error. This is reality telling us we do not understand something fundamental. Some argue the vacuum energy problem is the anthropic principle in action. Only universes with small vacuum energy produce observers. We exist, therefore we live in such a universe. No other explanation needed, but this is not physics. This is selection bias. It does not predict, it does not explain, it observes. Many physicists find this unsatisfying. They want a mechanism, a reason. A calculation that gives 10 to the negative 9 without tuning 120 decimal places. No one has found it. The string landscape has 10 to the 500 vacua, different compactifications, different flux configurations. Each gives different vacuum energy. Somewhere in there is a vacuum with our value. But finding it, calculating it, no one has done it. The landscape might explain why the value is possible. It does not explain why the value is ours. Might eliminate the ultraviolet divergence. Vacuum energy, finite from the start. But calculations are hard, not completed. Asymptotic safety. Gravity becomes scale invariant at high energy. Running coupling constant. Might make vacuum energy finite and calculable. Not proven. These approaches are decades old. Progress is slow. The problem is hard. Casimir force affects orbits of neutral atoms near surfaces. Precision atom interferometry. Might measure vacuum energy, gravitational coupling. Not done yet. Proposals exist. Nanotechnology advances. Room temperature. Casimir force measurements. Improved materials, metamaterials, engineered dielectric properties. Could test vacuum energy hypotheses. Small steps. The mountain is high. 2011 experiment produces 9.96 billion photons per second from the squid circuit modulating at 11 gigahertz. These are real photons. Energy approximately 73 microelectron volts per photon. Total power, approximately 7.3 times 10 to the negative 11 watts. Tiny, but measurable. Zero before modulation, non-zero during. The vacuum provided the photons. The squid provided the energy. Mechanism is quantum. The photons come in pairs, correlated, squeezed. Signature of vacuum origin. Classical oscillator could not produce this spectrum. Quantum field theory predicts it exactly. Observed. The dynamical Casimir effect is the most direct evidence that vacuum fluctuations are real. Different frequency range, different geometry, same physics. Vacuum fluctuations convert to real photons when boundary conditions change fast enough. Each experiment confirms theory. Each experiment probes different aspects. Each experiment rules out alternative explanations. The quantum vacuum is not going away. It is here. It is measured. It is used. Energy and time are uncertain. Borrowed energy returns quickly. The student asks, where does it come from? The professor says the question is wrong. Energy is not conserved in quantum mechanics for short times. Uncertainty allows violations. The student asks then, why does the universe not explode? The professor says, because the violations are small and temporary. The student asks why. The professor says, that is the theory. The student is not satisfied, neither are the physicists. But the theory works. Every test passes. Accept it and move forward, or stay stuck demanding why. Physics measures how. Philosophy asks why. Both are valid, neither is complete. It curves space-time, except we cannot calculate how much. We know it does something. We cannot calculate the biggest effect it should have. This is where we are. Decades of precision experiments, decades of theoretical work. The quantum vacuum is more measured and less understood than anything else in physics. The cosmological constant problem is not going away. It waits for someone, some idea, some experiment, some breakthrough. In 1947, Willis Lamb measured a gap that should not exist. The vacuum did it. In 1948, Hendrik Casimir predicted a force from emptiness. The vacuum does it. In 1997, Steve Lamoureux measured the force. The vacuum did it. In 2011, Christopher Wilson created light from nothing. The vacuum did it. The quantum vacuum is the most productive nothing we have ever studied. And somewhere in its fluctuations is the secret to dark energy, to quantum gravity, to the structure of space-time itself. We have measured the vacuum with extraordinary precision. We have calculated its effects to 12 decimal places in some cases, and we have miscalculated its largest effect by 120 orders of magnitude. This is not a paradox. This is a clue. The vacuum is telling us something fundamental is missing. We just have not figured out what yet, but when we do it, we'll change everything. Again.